the effective resistance of the squirrel cage rotor can be increased. So that is what we have done. And in that category, we have two types of squirrel cage rotor. One is deep bar rotor, another one is double cage rotor. Deep bar rotor, it means that if the depth of the rotor conductor is very large and if the frequency is very high or under alternating current condition, the skin effect is dominating there and we will get higher reactance in the bottom of the conductor and less reactance at the top of the conductor. So the reactance is uniformly distributed. Because of that, the current is non-uniformly distributed. At every point, if you measure the resistance, then the effective resistance of the rotor is observed to be increased. So that is what we have seen in deep bar rotor. Further, to improve the performance of deep bar, people have come up with double cage bar rotor. The concept is very similar to deep bar rotor, but they have done little modification in the deep bar rotor. Here, the rotor construction is very similar to deep bar, but you have two cages. You have two slot positions. One is upper cage, another one is lower cage. And in the upper cage, we'll have certain conductors. And in the lower cage, we have certain conductors. And both are connected. That is called as constriction. Both are connected together using one small rod-like conductor structure. That is called constriction. And the upper cage material is chosen in such a way that it has high resistance and low reactance. The upper cage has high resistance and low reactance. You have to choose your material in such a way that the upper cage will have high resistance and low reactance, and lower cage will have low resistance and high reactance. So the material is chosen like that. Here also, you have more crowding of flux lower part when compared to the upper part, and the skin effect here also it is there during starting time, because during starting time the frequency of the rotor is more when compared to the running time. So because of the skin effect, all the current in the rotor is pushed towards the upper part of the rotor. The concept is very similar to deep bar rotor, but here when all the current is pushed to the upper cage is having high resistance and low reactance. So because of this nature, see, already the effective resistance of the rotor is increased because of the skin effect. In addition to that, the upper cage is having high resistance when compared to the reactance. So, because of this, the effective resistance of the rotor is further increased. Right? Already the effective resistance is increased, and all the currents are pushed towards the upper cage, but upper cage is having high resistance. So the effective resistance of the conductor is further increased. So still the starting current is reduced, and that is better when compared to the deep bar rotor. This is what happening during starting time. Starting time, skin effect is dominating. Here also all the currents are moving in the upward direction. The effective resistance of the rotor is increased. In addition to this, upper cage already it is having high resistance. So because of this, the effective resistance of the rotor is further increased when compared to the deep bar rotor. And during running condition, there is no effect of reactance because the frequency of the rotor is very, very less. So the effect of reactance, it is not at all coming into picture, right? So only you have the resistance which is dominating than your reactance, and the current during running condition, no, it will go till end of the lower cage. Only during the starting condition, the current flows at the surface of the rotor in the upper cage. During running condition, so there is no skin effect, the current is not pushed upward, so the current is uniformly distributed and the current will flow in the lower cage also, right? So during starting time, the current will flow only in the upper cage, but during running time, current will flow both in upper cage and lower cage, because lower cage, it is having very low resistance, so the current will go, or the current will penetrate till the lower cage, because if it is not penetrating till the lower cage, during running time, the machine will have the poor efficiency, because the complete potential of the conductor will not be exploited, right? The complete potential of the conductor will not be exploited if we don't have low resistance in the lower cage. So during running time, the current will penetrate till the lower cage of the rotor. So conceptually, double cage rotor and deep bar rotor are same. Only thing, double cage rotor, you have two types of conductor made up of different materials to further improve the performance. Starting performance is improved when compared to the deep bar rotor, right? So this is your 3D diagram of double cage rotor. You can see here, this is your, you can see here, this is your lower cage, bottom cage or lower cage. This is your lower cage, and this is your upper cage. So they have cut and they have shown for better understanding. This is top cage or upper cage. You have two layers of cages, and in which the conductors are placed, and both the conductor, it is connected towards small conductor rods. You can see here, this is small conductor rod. So this conductor are conductors that will have different material, and this conductor will have different material. So initially the current will be flowing in the upper conductor because of skin effect, and during running current will flow in the lower cage also because it is having very low resistance. So that is the construction of double cage rotor. So that is what I have written here. Upper cage, high resistance. The material used is magnets in combination with brass. Area of cross section is more, so that it will have high resistance. And lower inner cage, that is having low resistance. The material is made up of copper. Area of cross section is less because it is having low resistance. Because of that, it is having low resistance. Similar phenomenon takes place as compared to that of deep bar rotor, but the starting torque is improved as compared to deep bar rotor, or in other words, starting current reduced as compared to the deep bar rotor because of effective increase in the resistance is more when compared to the deep bar rotor. So comparison of deep bar rotor and double cage rotor. So starting current decreases because the effective resistance of the rotor increases. starting torque increases because the rotor resistance is increased. From the torque slip curve, we have seen that the starting torque also will be improved, and these are all due to only the effect of skin effect. These are all due to only the presence of skin effect. That is what I have written in red color. All these phenomena will take place only due to the skin effect in the case of D-bar rotor. But in the case of double cage rotor, all these phenomena will happen not only due to skin effect, but also due to these two properties: low resistance and reactance in lower case, and high resistance and low reactance in upper case. Right? So this is your deep bar rotor and double cage rotor. As a summary, you have different starting methods: stator side and rotor side are there. Stator side starter, you have primary resistance, primary reactor, auto transformer starter, star delta starter, and the commonly used starters are auto transformer starter and star delta starter. These are all most popularly used starter, stator side starter. And DOL starter, it is also popularly used, but only it is suitable for low rated machine that is having the current less than 1 amp, or in terms of power, I can say that the machine which is having less than 1 HP, that starter is suitable, right? So when compared to rotor side, slip ring induction motor is having the provision to add some resistance external motor. If you add resistance, starting current can be decreased, and in addition to that, starting torque can be increased. That we understood from the torque slip characteristics, and this is possible only in slip ring induction motor. And people thought that why can't it is not possible in the case of squirrel cage induction motor. With that idea only, they have come up with two special modification in the rotor. So that is D-bar rotor and double cage rotor. So with this, effective resistance of the rotor, somehow they have improved. Right? So this is what the D-bar rotor and double cage rotor. And with this, the first topic in Unit 2 is completed. Starting method. Now the next topic in Unit 2 is speed control method. So what is the necessity of speed control? So it is very similar to DC motor speed control. Various applications need various speed ranges. So that is the first necessity. And the second necessity is comfort. If the climate is very cold, then you need to decrease the speed of the fan. If the climate is very hot, we will be increasing the speed of the fan. So these are all the necessity of speed control. And how to do this? For that, we have to see what are all the parameters on which the speed of the induction motor depends. So that we can understand from the definition of induction motor. So the first well-known speed equation is synchronous speed is 120 F by P, where F is the frequency, P is the number of poles. And from that equation, we can understand that if you vary the frequency, the speed can be varied. If you vary the number of poles, speed can be varied. And the second equation, we are taking the torque equation. The torque is proportional to S times V square. I can write the relationship like this from the torque equation. K is the constant of proportionality. From this, I can understand that if I vary the stator voltage, I can vary the torque. If I vary the torque, the speed of the machine automatically can be varied. Right? Automatically can be varied. So that is the second variable on which the speed of the motor depends. And the third equation is rotor speed equation. That is nothing but 1 minus S into Ns. 1 minus S into Ns. The rotor speed can be varied by changing the slip. So the speed can be varied by changing the slip also. Or if you want to merge equation 1 and 3, you can merge like this. NR is equal to 1 minus S into NS. NS is nothing but 120 F by P. And if you vary the frequency F, rotor speed can be varied. If you vary the number of poles, rotor speed can be varied. If you vary the slip, rotor speed can be varied. And another equation is the torque equation. So that is what the torque equation I have given there. Torque is equal to KSP squared R2 by R2 squared plus SX2 the whole square. Here, the linear region is very much important when compared to the nonlinear region. So the operating point lies in the linear region only. So if you approximate the torque equation for linear region, so I can write torque is proportional to slip into V squared. Torque is proportional to slip into V squared, and from that I can understand that if I vary the stator voltage, the torque of the machine can be varied, and in turn the speed of the machine can be varied. So based on this, you have different types of speed control methods classified into two categories. One is stator side speed control method, another one is rotor side speed control method. So in the stator side speed control method, the first method is if you vary the stator voltage or if you vary the supply voltage is nothing but stator voltage. So if you vary the stator voltage, speed can be varied. That we can understand from the torque equation. Torque is proportional to S into V squared. And if you vary the number of stator poles, so 120 F by P, speed can be varied. If you vary the frequency, stator frequency, speed can be varied. Or another control is that if you vary voltage, magnitude and frequency simultaneously, that control is called as V by F control method. Using that also speed can be varied. One, varying magnitude of the voltage, that is stator voltage control method. So here stator voltage control method is nothing but varying the magnitude of the stator voltage. Varying the, that is the meaning, varying the magnitude of the stator voltage. Magnitude of the stator voltage. And 2 is, that is number of poles, and 3 is varying the frequency of the stator voltage. And the fourth method is if you vary the magnitude and frequency of the stator voltage proportionately, then it is called as V by F control method. So these are all stator side control methods. Rotor side control method, you have two categories. One is adding resistance to the rotor. So rotor resistance control method, that is the first method, and slip power recovery scheme. So here, when you add resistance to the rotor or in slip power recovery scheme, the slip of the machine is varied. So in the rotor side control method, you have two categories. One is rotor resistance control method, adding resistance to the rotor. No? In other words, I can call like this: rotor resistance control method. Adding resistance to the rotor, no, I can call like this: rotor resistance control method. And slip power recovery scheme. That is one more method that you will see what is that. That is slip power recovery scheme. In these two methods, the slip of the machine is varied. Okay. Because the speed can be varied by varying the slip. The slip of the machine can be varied by adding resistance to the rotor and in the slip power recovery scheme. So these are all the various speed control methods, and we have to see this speed control method one by one. First, we will take stator voltage control method. That is varying the magnitude of the stator voltage. So this is called as stator voltage control method. So in order to understand this, in order to understand these data voltage control methods, we have to take the torque slip characteristics. Okay, we have to take the torque slip characteristics. Here, the torque slip characteristic is drawn for various voltage levels. Let me take, I am keeping stator voltage as V1 and I am drawing the torque slip characteristic. So you will get the graph like this. You will get the graph like this. This is for V1. Some value you can take. This is for V1, stator voltage magnitude value. You draw the torque slip characteristic. So this is the graph you will get for V1. Similarly, you draw the torque slip characteristic for another voltage value. Let me take this is V2. Let me take this is V2. Similarly, you draw the torque slip characteristic for, say example, another value V3. So if you draw the torque slip characteristic for various voltage values, we will get families of torque slip characteristics. So this is called as family of torque slip characteristics. Okay, and here V1 is taken as the rated voltage. V1 is taken as the rated voltage. Okay, and V2, that is lesser than the rated voltage. V3 is further lesser than the V2. So V1 is greater than, V2 is greater than V3. We cannot draw the torque slip characteristic with the voltage value more than the rated one, because we will get the insulation problem. So always we will draw the torque slip characteristic for rated voltage, and for reduced voltage only we can operate the machine, because if we operate the machine more than the rated voltage, then we will get insulation problem. So V1 is greater than V2 and that is greater than V3. And here you take the operating point, right? Operating point, actually no, it is lying in the linear region of the induction motor. And let me take the operating point of the torque slip characteristic drawn for V1 as 1. Okay, this is operating point corresponding to this voltage. Okay, and the operating point corresponding to this voltage V2, let me take it as 2. An operating point corresponding to this V3, let me take this is 3. See, generally here I want to define one definition for operating point, right? The operating point, that is the point with which the motor is operating. That is one way of understanding the operating point definition. The actual definition of operating point will go like this. Operating point is nothing but that is the point of intersection between the machine torque and the load torque. Okay, operating point, that is the point of intersection between the machine torque and the load torque. See, you take a motor is always coupled to the load. So this is my motor. The motor has to meet the load demand. For that only we are designing the motor. The motor will have its own torque characteristics. Every motor will have its own torque characteristics. So here we are choosing induction motor. So induction motor will have its own torque characteristics or torque slip or speed characteristics. Okay. Every motor will have its own torque speed characteristic. The induction motor also will have its own torque speed characteristic. Similarly, every load will have its own torque speed characteristic. Okay. Similarly, every load also will have its own torque speed characteristic. Right? Every load also it will have its own torque speed characteristic. Sometimes the torque speed characteristics of the load can be linear, or it can be parabolic, or it can be hyperbolic. That all depends on the type of load what we are using. In this example, I have taken the characteristics of the load is linear and it is constant independent of the speed. You see here, this is the torque speed characteristics of the induction motor. Okay. This is the torque speed characteristics of the induction motor. And this is the torque speed characteristics of the load which is coupled to the motor. Right? And this torque speed characteristic is having the property that it is constant and it is independent of the speed. You see here, whatever the speed variation is there, the torque of the load is constant. Right? So this is the load characteristic. So that is indicated in TL. So TL is nothing but load character. Here it is, instead of saying linear, I have to say it is constant. Here the load torque is constant, independent of the speed. Independent of the speed. So here, when the motor is meeting the load demand, at certain point, the load torque will intersect with the machine torque. So that is the operating point of the machine. Right? At certain point, the load torque will intersect with the machine torque. That is the operating point of the machine. Here, if you see the intersection is happening in non-linear region and it is also happening in linear region. I told you that people will design the motor in such a way that it will operate only in the linear region. So if you consider all those points, then the intersection of load torque with the machine torque in the linear region for various voltage values, it is here. This is 1, 2, 3. This is the intersection of load torque with the machine torque when the machine is operated with the voltage V1. And the operating point 2, that is the operating point of the motor. That is the operating point of the motor. So I have class. So that is the operating point of the motor. So this point 2, that is the intersection of load torque with the machine torque when the machine is operated with the voltage V2. And operating point 3, that is the intersection of machine torque with the load torque when the motor is operating with the voltage V3. So corresponding to the operating point 1, you take this speed. So this is the speed, that is N1. And corresponding to operating point 2, you take the speed, that is N2. And corresponding to the operating point 3, you take the speed, that is N3. You see here, N1 is greater than N2, that is greater than N3. So what we can understand from this analysis, when we vary the voltage of the induction motor, the speed of the induction motor is changing. That we can understand from the operating point. When it is operated with the voltage V1, the machine will run with the speed N1. When it is operating with the voltage V2, the machine will run with the speed N2. So whenever the machine is operating with the voltage V3, it will run with the speed N3. So this analysis already we have seen in unit 1. Effect of stator voltage variation on the torque slip curve. So why we studied that effect in unit 1? The application is speed control of induction motor. Right? Why we studied the effect of stator voltage variation in unit 1? The application is speed control of induction motor. So when you vary the voltage, the motor can operate at different speed levels, that is N1, N2 and N3. Right? So from this I can say that the speed of the motor can be controlled. So this we can understand only from the torque speed characteristics of the motor and torque speed characteristics of the load. Right? Sometimes no, the torque speed characteristics of the load, it can be like this also. Then this is the operating point corresponding to V1. This is the operating point corresponding to V2. This is the operating point corresponding to V3. Right? So it may have any characteristics. Right? I think the PPT closed. So like that we can understand the speed control when we vary the stator voltage of the induction motor. Okay. The next question is how to vary this stator voltage magnitude. So we understood that when we vary the magnitude of the stator voltage, speed of the machine can be varied, right? But how to do that? We can vary the magnitude of the stator voltage using auto transformer. Using auto transformer, right? So using auto transformer, no, you can vary the stator voltage. So whatever the graph I have already discussed, the same graph here they have shown. This is what I explained to you. Any doubts in that? And the advantages and disadvantages in stator voltage control method, no? The advantages and disadvantages. And before that, I show this graph to you. This graph is visible to all. Actually, the torque speed characteristics of an induction motor drawn using MATLAB simulation. So I have taken one motor and I have varied the voltage, and for various voltages, no, I have drawn the torque speed characteristics of induction motor. The rated voltage of the induction motor, what I have chosen is 450 volts. So the first graph I have drawn for 450 volts. Second graph I have drawn for 332 volts. Third graph I have drawn for 249 volts. And this is the operating point. 1, 2, 3. This is the hypothetical point that will not get when you simulate in MATLAB, because that is hypothetical, no? You cannot get that point. You have to extrapolate that point from the operating point. That is what I have extrapolated. So this is the torque slip characteristic of induction motor simulated in MATLAB. But here one thing you can observe that the torque, speed or slip characteristics, no, we have drawn very smoothly like this. But here if you see this region, no, it is highly what I can say, this is very highly, it is non-linear, and you have multiple peaks, and after that only somewhat this portion, no, you are getting. So this portion is this one, and this portion is this. So why it is too much non-linear? It means that when you simulate any system, no, not only induction motor, when you simulate any system, for some period of time you will have transient, right? So this kind of high non-linearity, no, till 500 RPM is coming because of transient of the induction motor, right? If you omit the transient, if you take only the average value, then you have to draw the trajectory like this. You have to take the trajectory like this, the starting torque, and you have to take the trajectory like this. Right? So you have to take the trajectory like this, or you have to take the average value like this. Right? So that is the steady state whatever I have drawn here, no, that is dynamic torque speed characteristic. Dynamic means it is having transient also, and whatever the graph it is shown here, no, that is steady state torque characteristic, right? Strictly speaking, actually this graph, no, it will come like this, then afterwards it comes like this. So if you take the average value of this transient portion, then only you will get the steady state torque speed characteristic. UG level steady state characteristics is more than sufficient than understanding the transient torque speed characteristics or dynamic torque speed characteristics. Okay, so just I want to share this information, because when you plot the graph in MATLAB, you will not get this smooth graph. You will get the transient part along with the steady state. You have to take the average of this graph. So just like this you have to draw. You have to start from here, then you have to take the average, then it goes like this. So that is what the graph is coming like this, right? So any doubt in this graph? This graph is torque characteristic, that's all. The transient also it is included. Whatever the graph we have seen here, that is steady state torque speed characteristics. You have to take only the average value. Any doubt? Yes. Now, what are the advantages and disadvantages in stator voltage control method? So, merits are, it is very simple. It is very simple, because using auto transformer easily you can vary the magnitude of the stator voltage. It is a very simple control method. But what is the demerit? The first demerit is starting torque keep on decreases. Starting torque decreases when you reduce the stator voltage. You see here, so this is the starting torque, and when you reduce the voltage, the starting torque decreases, right? And second disadvantage is it will not give wide speed control range. It will not give wide speed control range. What is the meaning of the second point? It will not give wide speed control range. Suppose, for example, for the voltage 450 volt, you are measuring the speed. You take the speed is 1440 RPM. You are just reducing the what I can say voltage to 250 volt. If you measure the speed, you will get around 1400 RPM. You see here, the voltage you are reducing more than 50%, but the speed reduction is not 50%, or it is not at all 20%, only 1440 RPM and 1400 RPM. That you can observe in this graph also. You see here, for 415 volts, this is the operating point. Okay, and for 332 volts, this is the operating point. And 249 volt, green color, this is the operating point. You measure the speed, it will be around 1440 RPM. You measure the speed here, right? Here the voltage is 415, here 332, almost 50% you have reduced. Here it is 249, more than 50% you have reduced. But the speed variation what we got, it is not that much. Or the speed variation, no, it is very narrower. It is not wide. Or the speed control range is very, very, very small. It is very, very narrow. This is the speed control region. Or this is the speed control range. It is very narrow. This is the speed control range. It is very, very narrow. So, the reduction in speed is not much in par with the reduction in the stator voltage. Or in other words, the speed control range is very, very narrow. The region is very, very narrow. Right? It is not wider. Suppose, for example, 415 volt, 1440 RPM, 332 volt, 900 RPM. The speed control range is very, very high. See, 1440 RPM, 1400 RPM, there is no much difference between 1440 and 1400 RPM. Almost the machine is assumed to be running at the same speed. You cannot find any difference in the speed. Right? 10 RPM, 20 RPM and all, how you can observe the difference? So sometimes most of the application, no, it needs wide speed control range. Right? If speed control range is very, very small, then what is the use of varying the voltage, or in other words, varying the speed? So that is major disadvantage in stator voltage control method. You will not get the wide speed control range. That is the problem in stator voltage control method. So with this, I complete the today's class.